thank you. Thank you yeah, this is a very nice place in Poland, I understand. And it's a very nice meeting over maybe 2.5 pandemic, and then the last year at the San Francisco area. Well, today I will talk about these topics. It's a photon radiation calorimetry. It's a different calorimetry which Jean-Paul introduced. Okay, let me start. Let me start from this figure. So this is an excess heat generation system with using the nickel copper nanofoils during hydrogen or deuterium gas disruption. The main point of this slide is that our sample is just isolated in the vacuum, and it is heated up by a high temperature up to say 1100 K. And then the sample starts to dissolve the gas. During the dissolution, we can measure the radiation from the sample this way or this way. So this is a typical excess heat measurement cycle, just one cycle day, one day cycle. During the night, the sample absorbs the hydrogen or deuterium, which is pressurized for a summer temperature around more than 10 hours. Then in the morning, we will go there and start measuring. And what's that? Evacuate the chamber and simultaneously to raise the temperature. By setting that sample at some of the temperature value, we each can control by changing the voltage or heat power. And then dissolution started. Radiation measurement also started. We will stay during the daytime, just measure in various conditions. And then after that, stop it. And then for the next day, absorption again. Why we measure photon radiation? An isolated sample at high temperature, all the energy is dissipated by photon. Photon radiation, the radiation from the sample is part of the total heat power from the sources. So this is a typical radiative power spectrum. You see that this is a typical radiant power spectrum. This is two spectra written by red curve and blue curve. The temperature measurement only is not enough because, for example, if you see the two compared to red curve, temperature is just a reflection of this slope, this part. So the red curve has high temperature than the blue one. And then you can say, oh, it's because of excess heat. But it is not true. In this case, the whole radiation power is the same. Q red equals Q blue. Why this happened? So when the emissivity is changed, the emissivity of a sample is changed, this can happen. That is, I would say, temperature rise does not necessarily correspond to the power production. And when the hydrogen gas is admitted, sometimes emissivity getting lower, then make a temperature rise. This is one thing. And two, are there any hot spots? If there, we can measure it and then we can search it. And if there, we should have seen the another temperature trend in this spectrum. So we find that we can measure it. The spectrum might show deviation from the thermal emission, like this. Number 3, is there a non-thermal electronic transition in the sample, like a band-like structure? around this part, or just the sharp transitions in this wireless region. I would say radiation emission is much faster than the thermalization. So that means if we find that, we can obtain the important information immediately after the reaction occurs. There might be lower states connecting between dense energy generation and thermalization. So this is our detection system. You see, we employ the three detectors essence. This is one is mid-IR, mid-infrared region detector. That just play as a power meter. And near infrared region, and also the visible light region. We connected these measurements to make one spectrum. Recently, we added two things here. One is another mid-IR, and this focusing lens here. Then what's happened? Measurements can be performed in the same condition without rotating the sample. Before that, we have to rotate the sample to get a whole radiation. But now, it stays there. It's a very good, eliminate the uncertainty of position due to the rotation. The quality of the data is improved, of course. And also, the mid-IR power meter is very nice because it has very short time response. It's every 1 second we can get information from these. You see, if you measure the radiation by these just two, that's a measurement of radiation improved with an improved time response continuously. That's the one. The other one is I just changed the sample holder. So before changed, we have this kind of things. You see, this is the sample region, and lots of holder space, which is made of photobill, I'd say. Those material reduced very much. You see, very fat, very thin. And then what improved is the ratio of the observing radiation to the power input is reduced very much. You see, if you put the input power, you say 20 watt for the system. In the old system, only the, let's say, 2.5 watt can be observed. But in this case, this is just from the sample radiation. In this case, ratio is much more. That is reduced photon radiation from the holder. So this ratio, observed radiation to the input power is increased very much. That means higher detection efficiency, which plays a role to reduce statistical uncertainties as well as systematic errors. Okay, this is how we evaluate the Excel system. You see, we have an isolated system in the vacuum, and there is a heat flow toward the chamber wall. One is QS, that's a radiation sample. We are observing this, and also holder, radiation from holder, QH. And the others are just a conduction heat loss from the rods, through the rods. This is actually very negligibly small. And the other one is the heat back from wall of the chamber. This is the radiation from the chamber wall, but it is again very small. So just neglecting these things, heat flow is in steady state, then we can write this equation. The Q total means just sum of this heat, and also the excess heat, if there is. And then the Q total is just constant times QS. QS is observed heat. So this is the essential to calibrate. For the calibration, just change the heater input is enough, because we don't care. We are observing this. We don't care where the heat flow comes from. Before this observation, that's okay. This is the point. So therefore, we have a calibration curve using this by determining changing the heater source. And one thing is we should remind is when the emissivity change over here, we have to change a little bit. Anyhow, it's a final form. Excess heat is just a proportion of observed QS times this quantity minus P in. Okay, experiment. I will show these two samples. The one is nickel to copper ratios change, nickel 1 to copper 3 on nickel substrate. The other one is no nickel and the copper. It's just a single layer copper on nickel substrate. And we change it. We use the two gases, hydrogen gas and deuterium gas. What we would like to know is, does excess power depend on hydrogen gas or deuterium gas? And also, does excess power depend on nickel-copper ratio? And how long does excess power generation continue? What a good time result detection tell us? Let's go. It's a radiation spectrum first. First of all, I would say the radiation spectrum is just described by gray body radiation approximation. It works well. Gray body means just the two parameters, emissivity and temperature. This tells you everything. And anyhow, if you compare these two, one side the nickel-copper ratio is 1/3, and the other side just a monolayer. You can say, yeah, the enhancement of the radiation is very much for this sample. Oh, by the way, I should say, so that this black X point is the radiation, just no hydrogen gas, no deuterium gas. And the another thing is, there are two red points, 2 points, two kind of points, color. Hydrogen with red, deuterium with blue. Can you see the difference? I would say no. So therefore, the enhancement of hydrogen and the deuterium is almost similar. But this enhancement, enhancement between the without gas and with gas is obvious. So this is just one graph, just glance of this change. Nickel substrate, almost same without vacuum, and change it to the ratio 5:1, immediately increases, and 1:3, as a little bit, and then almost nothing again. So let's say samples with nickel-copper composite layer show obvious excess heat, while those with monolayer of copper or nickel show excess heat very slightly. Let's compare more quantitatively. So this is the plot, excess power versus input power. So from here, the new measurement result. So before that, this is the ratio for 5:1, H2 gas and no gas and nickel alone. So we can say nickel substrate alone does not seem to produce excess heat if they are very small. And then if you compare the other one, monolayer copper to the nickel-copper composite. Complex and the monolayer copper slightly produces excess power. But there's a possibility of alloying with nickel substrate. That possibility can't be ruled out, so we don't know the answer. Anyhow, complex nickel copper layer certainly produces excess heat. Excess heat larger for nickel 5 to copper 1 than nickel 1 copper 3. But we should confirm this one with new measurement again. Okay? So how long does excess power continue? This is just short-term behavior. I would say, yeah, we repeated this kind of measurement, but repeating the measurement, the excess power increases like this. So this is the first period of hydrogen gas, and the next 3 or 4 weeks, we stayed deuterium gas and changed nickel gas again, hydrogen gas again. You see, if you compare this one and this one, the excess power is increased. But anyhow, we can say, oh, these three are different of input power, input voltage. But anyhow, we can say that excess power does not decrease in several hours, but seems to stay constant. And generated energy is increased by repeating the heat generation process. Okay, how long does excess power continues? This is a result of an 80-hour continuous measurement with 2 mid-IR detectors. I show here the two color data. The blue one is just a readout of 10-second interval, and the red one is averaged one. You see, if we look at the blue one, it's oscillating very much. Of course, this is averaging like this. And this is for the deuterium desorption, and this is for the hydrogen desorption. Almost similar quality of data are obtained. I would say excess heat does not decrease even after 80 hours. I guess this continues more and more, and is almost constant on average over time, although it is accompanied by large short-term fluctuations, as if it's oscillating. And I would say no significant difference in both. And using the initial value of the absorbed quantity of gas, in this case, 5 times 10 to minus 4 mole, and almost a similar quantity for this, then we can easily calculate the produced energy by just integrating this over, in this case, just 1.1 megajoule for the 80 hours. And the other one is 1.2 megajoule. And from this data, we can say that the minimum energy production for this case is just, for both cases, just around 10 keV per deuterium or per hydrogen. Okay? So, what is the QA excess power with a small amount of initial gas? Yeah, we have such data. In this case, the initial absorbed hydrogen is just an order of 10 to minus 6 mole. And this case is just 1 time 10 to minus 5 mole. And the produced energy is just around 0.5 megajoule. Then we can get this value. And maybe this value is the minimum value. It's always, should be always larger than that. But if you calculate the remaining hydrogen gas 8 hours after the start, which is estimated to be well below 1/10 of the initial value. If this is the case, then I would say energy produced per hydrogen is more than 4.6 MeV per hydrogen. No candidate is found in multi-fire reactions. For example, this is my calculation for thermal energy estimated by the various multi-proton reactions. 2 pKs, 3 pKs, 4 pKs. Anyhow, the 4 pKs is most largest one. But I would say it is just go to the 400 kV per proton. The point is, when the proton-proton reaction occurs, the neutrino takes off almost all the energy to the other ones. The contribution to the thermal is very small. Okay. So this is the conclusion. How about the dependence of H2 gas and D2 gas? There seems to be little difference. Similar amount of excess heat, about 4 watt, is produced for both. This fact appears. It appears as if chemistry is controlling the reaction rather than reaction rate. Whatever its origin is, we have suggested that E over H is larger than 4.56 MeV as a result of long-term measurement. And then no candidate is found in multi-proton reaction right now. And does excess power depend on nickel-copper ratio? Nickel-copper complex structure produces obvious larger excess heat than monolayer of nickel or copper. The film with nickel-copper 5 over 1 produces larger excess heat than the one with nickel-copper 1 over 3, but it needs more work. How long does excess power generation continue? Excess power does not decrease even after 80 hours. It is almost constant on average over time, although accompanied by large short-term fluctuations as it's oscillating. What surprises us is the constant excess heat production for more than 80 hours with a small amount of hydrogen gas. And finally, I would say the intensity measurement for mid-IR was able to record radiation change every second. The long-time behavior of excess heat changes from rather steady state to an oscillation-like state. This spectral measurement within a short period of time, I would say less than 1 second, is highly desired. This is our future next plan. Thank you very much.
Anyway, okay. Go to the beginning.
Which one?
Okay. Anyway, I tried to resume. You make experiment during a vacuum. The problem is static vacuum or dynamic vacuum. You have pumping when you make measurement, or just make vacuum, close the chamber and that. Yeah, this one.
Yeah.
Yeah. So it's a dynamic vacuum or static vacuum. There is a pumping when you make measurement or not, or just you close the chamber. After making vacuum, you close the chamber.
We're just pumping out.
Yes. And after close.
Just open the valve.
Continuously working. Okay, thank
Yeah,
you.
sure. During the measurement, we always keeping vacuum. Just
So
open.
keeping open.
Yeah.
Thank you.
The same recommendation to you, like in the previous speaker. This actually scheme which you showed there regarding getting a deuterium from 2 protons theoretically is possible. But if you do mass spectroscopy measurements of the outgoing gases, you'll be able to prove whether you have actually do synthesis of deuterium from both protons, which again theoretically is possible. So you must organize mass spectroscopy of the outgoing gases in your experiments.
Well, we are not measuring, but in the Yamamoto's experiment, they are measuring the outgoing gases. So essentially, to see the difference between proton and the deuterium is very much difficult. We're just making this mass analysis.
Yes.
Yeah.
Okay, now maybe somebody from our outside audience. I see here as Wushu Zhang. Could you hear me? You can ask a question if you want. No.
Yes. You may use the mixture gas or hydrogen and the deuteriums. For example, and 50% of deuterium gas, and you can try these mixtures.
I'm sorry, I cannot understand your
Could
question.
you ask once again? Very short question, no?
My meaning is I use the mixture of gases. For example, of hydrogen and 50% of you might try.
Did you try a mixture of gases?
Mixture gas?
Yeah.
No. Okay.
He suggests you should try a mixture of half hydrogen.
Oh, sorry, maybe the connection is not good. Not good. Okay.
So, okay, so there was no mixture of gases, anything. Okay, please, next question, please. We have still 2 minutes. No?
Dr. Kasagi, thank you very much for the interesting talk, Stephen Privet. And your conclusions, you spoke first about the similarity of results between hydrogen and deuterium. And you made a comment that, or you asked the question of whether, if you can get back to there, you mentioned something about chemistry. You said that it appears as if
I said as if it.
I was wondering if you
I'm
could
not
say a
saying
little,
this is a chemistry.
as if it
Yeah.
was chemistry.
Yeah. Is it the correct English for me, for you? I don't know.
Yes, I was just trying to understand a little bit more about what you meant by that. Thank you.
Well, yeah. Okay. We'll talk to Anna.
Okay, thank you.
Okay. Next person, please. Very quickly.
Professor Kasagi, quick question. What is the mass of the target? I think it's nickel copper substrate in the target section. How many grams?
Well, totally, maybe it is 0.1 gram order of 0.1, including substrate. Very small.
Thank you, Bob Green, Martin Fleischer Memorial Project. Thank you, Mr. Kasagi, Professor Kasagi. Point 4 on slide 2. Could you expand on the comment non-thermal electron transitions?
Oh, yeah. If there's a transition, for example, any transition is okay. For example, the collective motion of how to say, yeah,
Vibration? No?
yeah, cooperated the process of electrons and also the I just forgot the terminology.
Band gap.
Yeah.
Yeah.
Anyhow, band transition and something else that can be happen. So we cannot see we would like to see if there is or not. That's my question.
Okay.
Okay, thank you very much. Maybe one point for discussion during the coffee break. It's very surprising that neutrons and protons give the same energy amount. Not large difference because of the nuclear processes. We should expect some differences.
Yeah, that's true.
Okay.
I also.
Okay. Thank you very much once again.